That's this normal component, and that's just v dot n. So my more general formula is going to be like this. So the flow rate is going to be rho times v dot n times delta s. Okay? So I hope I convinced you that in this idealized situation where you have the uniform flow of this liquid, the velocity vector is the same everywhere, and the normal vector is the same everywhere, that the rate of flow is given by this formula. And now I generalize. Okay, but before I generalize, there's a question. Right, but n is a unit normal vector. I'm sorry, I should have said that. Right, the question is, I need to put here I assume that the length of this n is 1. So it's a unit normal vector. When I take the dot product, it's going to be the, oh, you're also saying this. Sorry, that's right, you're right, so thank you for correcting me. So the, first of all, I should have put the length of v, the magnitude of v, and second, I would normally have to also put the magnitude of this vector, but I assume it to be 1, to be equal to 1. It's a unit normal vector if you want. Okay, so now we're ready to generalize it. We generalize it by saying that it could be arbitrary membrane, and also the velocity could be different in different places. The velocity would just be given by some vector field. Okay. So what answer are we going to get now? It's the same idea as in the case of our calculation of the surface area. We break a general membrane. We break a general membrane into small pieces, and for each small piece, we apply the idealized scenario, where we assume that approximately the velocity is the same everywhere, okay, and the normal vector is approximately the same everywhere. So then we use this formula. But after this, we have to take the sum over all of those pieces, and when we take the sum, we take the limit when the partition becomes finer. And that's what gives us the integral of the second type. And you can read off the expression for this integral from this formula. As always, just look at the formula for the elementary calculation, which we get from the idealized situation, okay, like this, and just replace delta s by ds. Where now we already know what ds is, because we are able to calculate ds by using parameterization, by using this Ru cross Rv. Right? So general membrane, the flow rate, just looking at this formula, is, and let me put rho outside, because rho is just a number. It doesn't depend on, actually, I mean, might as well depend. So let me do something else. Let me say that f is rho times v. The density, the mass density function could, of course, in general be non-constant, that's fine, and the velocity vector field is non-constant. But let me just isolate this, the product of the two as a particular vector field. This formula will be nicer this way. So then, well, if I do that, this can be written as f dot n dot times delta s. So what I end up with is an integral over m of f dot n ds. Okay? But now, what is n? Now, I would like to make sense of this integral by using a parameterization. You know, this is already a definition, right? Because once I take the dot product, I start with a vector field, but my surface has its own vector field attached to it. It's a kind of an inherent vector field attached to the surface, namely the normal vector, unit normal vector at each point. And I take a dot product and I get a function. And functions I have already learned how to integrate. You see, since I've learned how to integrate functions, this actually already makes sense. But let me spell it out in more detail by using parameterization. So suppose now that my surface is actually parameterized in this way. Then I can actually find a normal vector, and the normal vector is going to be precisely this Ru cross Rv, which we have used here. This actually, as a vector, it is normal to the surface at this point. It is normal because, remember, as I said, in this calculation, you have to take a cross product of two tangent vectors. When you take a cross product of two tangent vectors, you get something perpendicular to them, and therefore perpendicular to the surface. This is a normal vector. This guy is a normal vector. But in the previous calculation, we just took its norm, and we saw that the norm is this. So this gives me a way to actually get my formula obtain a very explicit formula, because this is a normal vector, but unfortunately it's not normalized, which is a horrible pun, right? So it's normal in the sense that it is perpendicular, but it's not normalized in the sense that its norm is not equal to 1. But now I will normalize it, so we'll get a normalized normal vector. Okay. I think it's because our language and our everyday language is too poor to express some mathematical concepts, you know, and that's why it sounds really bad. But so let me just write a formula instead, without saying anything more. The formula is that n is Ru cross Rv divided by its magnitude. If you have a vector and you divide it by its norm or magnitude, you obtain a vector which has norm 1. Right? It's always the case. So this is what I should put here instead of n. And also instead of ds, I have to put my old formula, has already been erased, but I want to remind you, maybe here, that the integral over m of f ds was equal to the integral over d, where d is this region, of r sub u cross r sub v dA. In other words, sorry, and I forgot the function f. So in other words, ds becomes dA times this guy. So what's going to happen now, and it will have a very nice constellation, we will have double integral over d of f dot ru cross rv. Then we'll have to divide by this, Ru cross Rv. And then we'll have to multiply by Ru cross Rv dA. Do you see? So it's kind of lucky because the same quantity appears in the numerator and denominator. And it's non-zero. This is actually something which we have to take care of because it should be non-zero, because otherwise it would not be a parameterization. This is like, think about this as like a Jacobian. It is a Jacobian, if you think about it. It is a Jacobian. And in fact, not surprisingly, the formulas we get for it, say for spherical coordinates, is a Jacobian. Right? It's not a Jacobian. And the Jacobian should be non-zero. For otherwise, this is not going to be a good parameterization. So that's why it's non-zero, and we have the right to cancel them out. When we cancel them out, we finally get a very nice formula. Namely, we get this. And finally, we have come up with a definition of the integral of a vector field of a vector field across a membrane, across the two-dimensional surface. If the surface is parameterized by a flat domain D, this integral is simply given by this formula, by this double integral over D. Okay? What it is, on the other hand, what it is more in a more canonical way is an integral over M with respect to the measure of the surface area of this function f dot M. But since we don't want to write it each time, we will actually write it. We'll use a new notation for it. We will call it f dot ds, where we put ds over ds, we put an arrow. In other words, we say that ds as a vector, by definition, is n times ds. If we do that, then we can combine these two guys into single simple ds with a vector over it. And what we're doing is we're taking the dot product of f with ds. So let me summarize. We're trying to understand what to make of an integral of a vector field across a membrane. And a good analogy is a line integral of a vector field. In the case of a line integral vector field, we had a different interpretation, because in the case of line integral of a vector field, it was all about pushing something along the curve. So what mattered was the tangential component of the vector field, tangential to the curve. What matters now is the perpendicular component, because we're talking about the flow. The flow through, not along the surface. There's no such thing as a flow along the surface. It could be something along the curve. You cannot have something along the surface. It has to be across the surface. If it's across the surface, what matters is the perpendicular component, the normal component, which is what we get by taking the dot product of our vector field with n. So we're trying to find this, and this is called the surface integral of a vector field, or a flux of a vector field, through or across the surface. And this is very important. It's not along, it's across. This is an important thing. An important distinction between curves and surfaces. For curves, you go along the curve. For surfaces, this is a membrane. You go across the membrane. Okay? And that's why it's a dot product with a normal. And so this integral is given by this formula, f is a vector field, and the meaning of this integral is given by this formula. Once you parameterize your membrane M by domain D, like here, you can actually evaluate this integral in a very straightforward way by simply taking this cross product and taking the dot with f. For example, let's suppose that we are in this situation. We are in this situation where our u cross rv is given by this formula. This, I recall, is the situation where M is part of the graph of a function f. Okay? So, and your vector field f, say, is some pi plus qj plus rk. In this case, we can use this formula. So what we have to do is we simply have to take the dot product of this vector and this vector. And so what do we get? That's going to be the integral over d of minus p f sub u minus q f sub v plus r times dA. Very explicit formula. You have, if you have to do a problem like this, you're given everything you need. You are given the vector field, PQR. You are given your parameterization. In this particular case, although I have to warn you, this is a very special case when the parameterization is like this. This is the case when your surface is part of a graph. Right? So you're given function f. All you need to do is to find the partial derivatives of f with respect to the two variables. Right? And after this, you assemble all of this data into this formula, and you get a double integral. And double integrals you know how to do. You use any method you like. In fact, I wanted to do an example, but okay, well, maybe let's do a very quick example, just to see how this works. And then I actually have something to show you. Something fun. Note that this has not been fun. I have to say, the way I present this material is not the most economical, and I feel a little awkward because it's not the best possible way to present it. It looks a little bit ad hoc again because first you introduce the surface area, that was fine, surface area was fine, and the mass is fine, but defining this flux in terms of the surface area integral, the first type, that's not the most optimal way. So there is a much nicer way to explain this, and I will explain it, if not next week, then during the review lecture for sure. So I will give you a much nicer perspective on this type of integrals, and then you will see right away where these formulas come from. It will not look anymore so ad hoc. But for now, this will suffice. This will give you a reasonable definition which you can work with, and you can calculate fluxes in the surface integrals very easily, like in this case. So here's one example. Find the flux of the vector field f, which is minus xi minus yj plus z squared k. And S is part of the cone, z equals square root of x squared plus y squared. Between the planes, z equal 1 and z equal 2. Okay? So let's do this calculation. First of all, in this formula above, let's just say u is x and v is y. I mean, after all, in this particular case, we don't have to pretend that this is some new variable, some auxiliary variables. These are our x and y. So in this case, the function f is this. This is f of x, y. So I'm just substituting in that formula. So what I get is that f dot ds over this membrane. And by the way, it's very easy to draw it. So this is a cone. We're talking about the cone like this, and you use the part which is confined between two planes. So it's this one. I mean just the surface of the cone, but between this plane and this plane. It's equal 1 is equal 2. Okay. Think about ice cream cones. So this is going to be the integral over, under this, we'll have to do parameterization. And the natural parameterization would be by its projection onto the xy plane. And under this projection, this will go to an annulus. Somebody said annulus, right? Very good. This goes to, you don't have to say it quite so loudly. Anyway, so you get this annulus, and then you have to integrate over this annulus. And annulus, of course, has a very nice parameterization, which is that you have r and theta, polar coordinates, r between 1 and 2, and theta is between 0 and 2 pi. Right? So you can always convert this into integrated integral very easily. Right? But now integral of what? We have to take the dot product of p f sub x. So what is p? P is negative x. Right? And for some reason. Right, so when you do that, what you're going to end up with is negative x. So you first of all have an overall negative sign. Then you have negative x. That's this negative x. Then you have to take the derivative of this, right? You have to take the derivative of this. And the derivative of this, you know, as well as I do, it's x divided by square root of x squared plus y squared. Then the next one is negative y well, first of all, it's minus, overall minus, because there is an overall minus here. Then you have to take this negative y, and the derivative, which is y divided by square root of x squared plus y squared. And finally, you have to take this times just take the c squared, right? Why did I want to? I think that let me make it a little bit easier. So I write it like this. So you have the last one is z squared divided by square root of x squared plus y squared. Actually, no, it's okay. Let's just do it this way. So you get plus z squared dA. Okay. And after this, you have to substitute the square of this in here. So that will be just x squared plus y squared. So here you got a very simple formula, which you can now a very simple integral. You can of course take the sum and then you cancel out. You get square root of x squared plus y squared in the numerator. Here you get just x squared plus y squared. So you just calculate it by using the polar coordinates. Very easy. So this is how you do it. Okay. Now there is one issue which is left unanswered here, and that is the issue of the choice of this vector n. Let me illustrate it in this example. In this example, we are talking about this surface, right? This y. But now the point is, which n? Which n am I talking about? Am I talking about this n, which goes downward, or am I talking about this n, which goes upward? Okay. So there is this one issue which we have not yet talked about, and to make everything precise, we have to, in other words, to make the definition work, we have to say which normal vector we choose. And the proper terminology for this is orientation. This unit normal vector to our surface, or unit normal vector field to our surface, is called orientation. It tells us sort of which side is the front and which side is the back. Okay? And as always, there are two different choices. It's kind of parallel to the choice of orientation of a curve. But again, for a curve, orientation goes along the curve, and for a surface, it goes across, it's perpendicular to the surface. There are two different orientations in this case, and we have to say which one. So always, on the problems which you will solve on this homework, it will have to say which orientation you have to choose. When it says downward, it means that the z component of the vector is negative. When it says upward, it means that the z component of the vector is positive. In this particular case, we use the normal vector for which the z component is 1. So that means that this formula refers to the upward orientation. Okay? And then, of course, the really fun part, which unfortunately I don't have time to talk about, is about surfaces which have no orientation. And this is something really cool, which we'll have to talk about next week. But for now, happy Thanksgiving and see you next week.